All right, folks. 8-2 vectors. So now we're talking about vectors in the coordinate plane. So we're going to do some operations with these vectors in the coordinate plane. Shouldn't be too bad today, and a lot of it's kind of strategies we've used before. So we'll talk about that, and we'll practice. All right, so first thing, when we think about vectors on a coordinate plane in standard position, using the terminal point x comma y, like coordinates, the vector is symbolized by this. So it's kind of like a coordinate point, but we've got like the parentheses are like little kind of brackets, like angles there. They have a little sharper angle there on the sides there. And this is called component form. Okay. So if we look at the diagram here below, you can see that x, y, and just like you're going this way on x, you're going this way on y, and so this point would be x comma y. We think about that as vectors. Same thing in the coordinate, we just use a little different symbol. Okay, and here's some other ones. You can see these are all equivalent vectors. You can see they're all 3 on the x and up 2, but they would be in different points based on where they're at, right? That one is here, this one would be here in component form. So although they're equivalent, or they're traveling to the right 3 and up 2, they're on different points on the coordinate plane. All right, so let's talk about component form of, get that out of here. Okay, component form of a vector. All right, so in this case, you've got AB. How do you find it? You've got those 2 points, and basically you've got an initial point, and then you've got a terminal point. And so we can find it by just subtracting our x's and subtracting our y's. So it's a lot like slope, right? X minus x, y minus y, except we do our x's first here. So again, if you've got your x1, y1 here, and your x2, y2 here, you can easily find it by subtracting your x's and subtracting your y's, and that would get a component form. So we'll practice that as well. Now, if you want to talk magnitude, finding the magnitude is like the distance formula. So it's all stuff we've done way back in algebra. So if V is a vector, the initial point x1, y1, and a terminal point, and again, just remember what we talked about those. Your initial point is here, and your terminal point is over there. The initial point is where it starts, terminal point is where the tail is. So in this case, we have those 2 points, the initial point right here, and your terminal point right here, x1, y1, x2, y2. You can find a magnitude by doing basically the distance formula, okay? Magnitude is denoted by like the absolute value sign. So you've got the square root of x2 minus x1 squared plus y2 minus y1 squared. If it's already in component form, so if you already have the vector in this form here, then you could just simply take the square root of a squared plus b squared. So there's some problems where you'll already have it in vector form and component form, and then you can just kind of square the first one and square the second one, add them, take the square root, and you're good. Okay? All right. So continue. Let's do some practice with that. So let's find the component form of AB with the given initial and terminal points. So they give us our points. So it's simple stuff here. All we have to do is, again, remember, we're just taking, for these problems, x2 minus x1, comma, y2 minus y1, and that would be our vector. Okay, so in this case here, x2 is 6, so we're going to go 6 minus a -2. Just got to be careful with our negatives here. And then we've got 1 minus a -7 for our y value. So we can do the math here. Choom, choom. That makes 8. This makes also 8. So our vector in component form would be 8, comma 8. Okay. All right. Same thing over here. When we take our x2, it's -9 minus 0, comma -3 minus 8. And away we go. We can see that it's -9, -11. Just be careful with your negatives, just like we did back in algebra. All right, so the next one says the magnitude. So magnitude is like the distance formula. So you're just going to take these points and plug them into the distance formula. So remember, for these, we're looking at the big square root, and then it's x2 minus x1 squared plus y2 minus y1 squared. Okay, so for those problems there. So let's look at this one. So this one here, number 2a, you'd go 6 minus a negative 2 squared plus 1 minus a negative 7 squared. And then we can do the math inside. I know I can choom this one, so it's 8 squared. And then here is another 8 squared, which then gives us 64 plus 64 is the square root of 128, which is about 11.3. All right, and let's do this one here. Okay, so I mean, I know we're using the same points from the above examples, so you can easily kind of jump to that, but I'm just kind of doing the work for you. So negative 9 minus 0 squared plus negative 3 minus 8 squared. So then you're going to end up with negative 9 squared plus negative 11 squared. And that's where I talked about, you kind of just take this vector, right? This kind of connects it from A, B. We'll talk about that in a second. Just finish this problem up. And you end up with the square root of 81 plus 121. So squaring always makes something positive, which equals square root of 202, which is about 14.2. So there you go. Okay, so let's just connect that, right? So if we look at why it was already in component form, so you use the same examples here. 1a and 2a are the same examples, right? So if we just look at that, and same with 1b and 2b are the same points. So we already found component form, so that just kind of shows you, like, if I just took this here, the 8, and I could plug it in right here, right? The a squared plus b squared, essentially, that's what I'm doing if I already have it. I can kind of go right to here and get that done if it's already in component form. Same thing on this one, since I have the negative 9, negative 11 in component form, since they're the same points, I could have just jumped right to here and squared it. That's why this works right here, okay? Okay, so let's continue on. We just found the magnitude and move on to the rest of it. All right, so now vector operations. We talk about this one. So now you've got a couple vectors, A and B, and K is scalar. Then we can do the following things. So we know that this is true. If we want to add them, we just add our A plus B, the first one. We add the A2 plus B2. So add the first coordinate, the second coordinate, and you're good to go. Same with subtraction. So this is pretty easy. And then multiplication, just like in matrices, scalar multiplication, you're going to take that scalar multiple, K, and you're going to multiply it by both numbers in the vector. Pretty simple, okay? Now we can do the operations as follows. So let's practice those. We've got W, Y, and Z here, so let's go through it. All right, so let's start with 4W plus Z, number 3A. So 4W is going to be 4 times this vector here, negative 4 comma 1, and then plus Z, which is over here, negative 3, 0. Okay, so I'm going to do the multiplication first, and just again be careful with your positive negatives. It doesn't matter if you change the sign before or after. If you have a subtraction, well, it's all going to work out. Okay, so let's multiply here. We've got negative 16 comma 4, and then we're going to add this to negative 3, 0. So now I'm just adding these two up. So negative 16 plus a negative 3 is negative 19. And then adding these, 4 plus 0 is 4. All right, awesome. Now, next one. So if we look at 3b, I've got a negative 3 times W, which is negative 4, 1. So pretty simple. I just multiply them both. That's going to be negative 12, comma negative 3. And that's it. Okay. Next one, we have 3 operations here. So we don't have to be scared of this. We're fine. 2 times W is 2 times -4 comma 1, because that was this one here, plus 4 times Y, which is 2, 5. And then plus, or excuse me, minus Z. Minus Z, which is -3, 0. Okay, so I'm just going to kind of work through the multiplication first. So here I've got -8 comma 2, because I multiplied that one. Scalar multiplication. Over here I'm going to have 8 and 20, because 4 times 2 is 8. 4 times 5 is 20. And then I've still got this -3, 0 that I have to add over there. So now I'm just going to kind of add or subtract from left to right. And I go ahead and do that. -8. So my first one is going to be -8 plus 8 is 0 minus a -3. So I'm just going to choom there to make it a +3, right? Just going to not do that just real quick, just to keep it with the negative. And then the other side, 2 plus 20 is 22, and then minus 0 is 22. So 3 comma 22. Again, just be careful with your positive negatives. Make sure you double check there. All right, the last one. So those are pretty easy. The last one's the stuff that takes maybe the most time, but it's really not that bad. So let's explain what it is, and we'll do practice on it. So unit vector is a vector that has a magnitude of 1, okay? And to find 1, we can basically divide a vector by its magnitude, right? That's by that symbol. So these two formulas kind of give it to you right here, and we'll work with those to solve it, okay? And remember, if you have a unit vector, just a couple things, if you unit vector in the direction of a positive x-axis, it's a unit vector, so magnitude of 1, we represented it by this, I, which is 1, 0, and a unit vector in the direction of the positive y-axis would then be 0, 1, and we represent that with a j, okay? So as we go through here, the unit vectors in the direction of x and y are denoted by that. We just talked about it, I and j. And this kind of just proves how that works. So you've got, a unit vector here on the x is this one. The unit vector y goes up here, right? And then when you multiply them, they'd be standard unit vectors that we talked about here. But as we keep going, we can use any vector in this form, AI plus BJ, and what that does is kind of helps us to find that. So here's the kind of the proof of it, and we can work through it. If you have AB, and then you write it as a sum of two different vectors by adding those zeros in there, and then you multiply it basically by the I and J, you end up with your AI plus BJ. So this sum, and that's the proof, just kind of, you'll use that later, but when we talk about a linear combination of vectors I and j, that sum, AI plus BJ, is the linear combination, okay? So in this case, you look at 8, 2, 4 here, you've got, here's AI, here's BJ, so when you combine those, that's when you get this vector there, AB, okay? So linear combination there. So think about that, and this one, it looks crazy, but it's pretty easy. You just take the vector you have and then plug it into this right here, AI plus BJ, and then it's kind of, you're done, all right? So let's practice a couple of those. So let's first find the unit vectors with the same direction of the given vector. All right, so we want a unit vector. So what we're going to do here is we're going to take our u, and I like to use this equation that we got from back here. Okay, and I like to use this one because it's just easier to work through as we multiply it later. So I'm going to go 1 times the magnitude of v times v. Okay, well, in this case, it's w, the vector, right? So actually, w is what you're using. So what we're going to do here is we're going to go 1 over the magnitude of 6, negative 2, and then later we'll multiply it by 6, negative 2. So the reason I do it like this equation here is because it just helps avoid confusion. Later on, you can just use this part of the vector and multiply it, and you'll get your coordinates. Okay, so we got some work to do. We got to find the magnitude of this vector here. Well, remember that this is already in component form. It's already in AB, so I can simply just use this, a squared plus b squared, and take the square root of that. So what we end up having then is we're going to have 1 over square root of 6 squared plus minus 2 squared. And then later, again, like I said, we're going to multiply by this 6, negative 2. Okay, just kind of basically scalar multiplication. All right, so what does that come to? That comes out to 1 over the square root of 40, right? We've got 6 squared is 36, plus 4 is the square root of 40, and then we've got this 6, negative 2, okay? And as you get better at this, you can kind of skip ahead of steps, and that's fine. So now, I also have to remember that we've got square root of 4. So now here's where I'm going to multiply, and then we'll talk about square root of 40. So I'm going to multiply 6 times 1. So I'm going to have 6 over the square root of 40, comma, negative 2 square root of 4 over the square root of 40. And all I did there was multiply this by our left side here, which is just a 1. So that's why it kind of makes it easier. So I already have this as my new vector, basically, okay, or my unit vector. All right, now we just have to remember that square root of 40, we have to rationalize this. So we have to kind of take this from here, and I'm just going to rationalize the square root of 40. All right, so when I do that, and then I also have to remember that the square root of 40 is actually equal to 2 times the square root of 10, okay? So when I rationalize that, I'm going to have a 40 on the denominator, right? I'm going to take this times the square root of 40 and then times the square root of 40 on the top and bottom. So like I said, remember that this is like 2 times the square root of 10. So on the bottom, I'm going to have 40 because square root of 40 times square root of 40 is 40. So my denominators are going to be 40. So now what I have is I have 6 times 2 times the square root of 10, which is 12 times the square root of 10. Over 40, okay, comma, now I've got this negative 2 here times 2 times the square root of 10, which is going to be negative 4 times the square root of 10 over 40. Now I'm almost done because is there any reducing I can do? Sure, because 4 goes into both of those. 4 goes into 12 3 times, so 3 times the square root of 10. It goes into 40 10 times, so that would be one of them. And the other one would be 4 goes into both of those, negative 1, so negative square root of 10. 4 goes into 40 10 times, and away we go. So that would be our unit vector. Okay? All right, let's do the other one. Okay? And maybe we can go a little faster through some of the early stuff. Right? So what I'm going to do is I'm going to the unit vector. I'm saying 1 over the magnitude of this that they gave me, negative 4, negative 8, times negative 4, negative 8. And I'm just kind of placing that over there because I'll use that later. All right. So now it basically becomes 1 over negative 4 squared plus negative 8 squared, all under the square root because that would be the magnitude of it. And then we're going to multiply by this later on. Okay, so 1 over, this comes out to, that's 16 plus 64 is 80, so 1 over the square root of 80. Don't forget the square root symbol. It doesn't go away. And then you're multiplying by this as well. Okay, now I can go ahead and say, do my scalar multiplication here. So it would be negative 4 over the square root of 80, comma, negative 8 times the square root of 80. And then what I would have to do is just remember that, just a little side note, that the square root of 80, just put that over here, square root of 80 equals 4 times the square root of 5. Okay, when we rationalize that, it would be 16 times 5 in there. 16 is perfect square, you should pull out the 4. So now, when I rationalize this, I'm going to have 80 as my denominator because I'm multiplying by those. So I can basically take this part here, multiply by my numerators. So I end up with negative 16 times the square root of 5 over 80. Because remember, I'm multiplying by these. Okay. And then I'm just remembering that this part here, to make it a little easier when I multiply by those numerators. So then negative 8 times 4 is negative 32 times the square root of 5 over 80. Now I can reduce as we go. So reducing this becomes, I believe 16 goes into both of those. So this would be negative square root of 5 over 5, comma, this would be negative 2. 16 goes into both of those as well. Square root of 5 over 5. And I guess I should put vector symbols there, and that is my answer there. And these need vector symbols as well. And there you go. Okay. All right. Last one. And these are pretty simple here. So like I said, this is the linear combination. Right DE is a linear combination of the vectors I and J. All right. So I just kind of have to put this into component form. So I'm just DE in component form would be 2 minus a minus 6. And then 5 minus 0. Remember, it's just x minus x, y minus y. So that would equal 8 comma 5. And then I just kind of have to take the A value and the B value and multiply them by I. So it's really just 8 times I and the B value times J. And that's it. Right? We're using I and J. Okay? Same thing here. If I'm looking at DE, I want to get it into component form. So it's just x minus x, negative 7 minus a negative 3, comma, y minus y, which comes out to negative 4, comma 9. And then again, I'm taking those values of the vector. My A value is negative 4, my B value is 9, and writing it is AI plus BJ. So it's just negative 4 times I plus 9 times J is my linear combination. Simple as that. Okay, that does it. So I know it was a long one, but pretty easy stuff. Just, make sure you can deal with your positives and negatives, and you'll be fine. Okay, we'll see you next time.